Yes, you can start.
Okay, thank you very much. Um, so as you as you have noticed, yesterday I started kind of a new part of the lectures, the second part, which is more about geometry, geometric features, uh, and I first want to talk about cluster algebras from surfaces. So the topic of cluster algebras will still be there, but we slowly introduce these notions on surfaces. Uh, this is kind of a good way to move into the geometry part, yeah. And that has been developed really in a paper by Fomin, Shapiro, and Thurston in 2008. Uh, there's a There's a Fields medalist, Thurston, but this is not the one. It is his son who was author of that paper. And I'm just trying to kind of get a hold of who is there. There's one participant from Poland. Hello. Thank you for, and good. Okay, so what I want to say is that uh, at any time we kind of start a new topic, and I don't want to get lost towards the end of the week. So at any time, if you have questions, if you want to know something more in detail, please interrupt me. Please feel free to ask a question. Ask a question in the chat, and we can talk about this. Okay? Good. So we are dealing with marked surfaces, so with oriented compact surfaces like so, and we cut out a number of disjoint disks, and on the boundary of those disks, on those circles, we want to glue some, we fix some points which are called marked points. Okay, this is our setup. This is what we had discussed. Uh, Such a thing is a marked surface. Mm, examples, the simplest examples of marked surfaces is a disk. And I do allow myself to bend the disk to transform it so I can view this as an actual polygon, or I have a disk, a sphere cut out two disks, then this is an annulus or a cylinder, however you prefer. And then we had discussed the notion of an arc. An arc is a continuous curve in the surface that satisfies certain rules. First, it has to start and end in one of the marked points. By the way, I always consider arcs up to homotopy because I want to have a small number of objects as possible. So two arcs that are homotopic, I would identify them. Yeah. Um, the other very important condition, why does this happen? The other very important condition is that the arcs do not intersect, they do not have self-intersections. Yeah. So arcs that go around and intersect themselves 100 times, such curves are not arcs. The only exception that I do allow is at the endpoints. Yeah, I can start here in my surface and I walk around a little bit and I go back down there, but then I might come back to the same endpoint. This is allowed. Uh, yeah, this is are the most important properties. And I think this is where we ended yesterday. So, yeah, it's written here, December 20. So let's start. Now, the important notion for today is that of a triangulation of the surface. So, gamma, a triangulation, can be defined as a maximal collection of arcs that do not intersect, that are pairwise non-intersecting. Uh, all the time with the same idea that two arcs, they are not allowed to intersect kind of in the interior. They might intersect on one of the mark points at their endpoints. They can join. Yeah, this is what I would not call this an intersection. Okay. Okay, so let's give ourselves some examples. Let's start with the disk to really get into this topic slowly or smoothly. So in the disk case, I'm here. I can add some arcs. So let's add that arc here. Then I want to add some other arcs. So I want to connect it to this one, right? And I can add another arc here. So I have already three non-intersecting arcs. Now, important questions. Are there any other arcs? Yes. Where do you see those arcs? So maybe I help you to give an answer. Let's label the mark points 1, 2, 3, 4, 5,
The
6. So
boundary arcs at
the boundary
1.
arcs, yes. Of course, I tend to ignore them, but they are there to form a triangle. You're perfectly right. I don't even want to give them the same color. So there is an arc from 1 to 2, the boundary arc, and there's an arc from 2 to 3, also a boundary arc. And now together with the diagonal arc here, they do form a triangle. Yeah, a triangle, you need to be a little bit flexible with what we call a triangle. I mean, this is not an actual triangle by straight lines. This is just a sequence of three arcs, 1, 2, 3, and I come back to the point where I started with. Yeah, so in the interior of this is a triangle. Good. So of course I do add all the boundary arcs, this one, this one, this one, that one. And what I observe then I cannot add any more arcs. Yeah, I reached a maximal system, a maximal collection of pairwise non-intersecting arcs. This one is a triangulation. That's good. There might be for the same shape. Let's go over here. I mean, there's many different triangulations. I might, for instance, pick uh, the same two arcs here, and I can go here diagonally like so. And this is also a triangulation, yeah, because you do see I have a triangle here, 1, 2, 3. I assume the boundary arcs are always included, okay? I don't even draw them anymore. They are there, they are the boundary, okay? So I have a triangle here, I have a triangle here, I have a triangle here, and there's a triangle in the middle. So this is a perfectly fine triangulation. And so that example here just there to illustrate that uh, in general you can choose uh, many different ways to form triangulations. We are not yet there, right? I mean, there's still a quadrilateral, so I need to introduce one more arc. Let's go like this, and then I believe I have a triangulation. Okay, so you can, uh, and this is important, you can start with any arc between any two marked points, and then you just continue to add more and more arcs until you cannot add any more, and then you have a maximal collection and you have a triangulation. So every arc can be kind of embedded or extended to a triangulation. Every arc is part of some triangulation of that marked surface. That's okay. Mhm. Okay, so these are my examples. Oh no, I have got some more ambitious examples. Can you help me? Here are my two boundary arcs, 1 and 2. Uh, I have some, let's get this out of the way. I have some boundary arcs. So here is one boundary arc, and I have another boundary arc, this one. These are the only two boundary arcs. So what, do you have some suggestions? Give me some arcs.
1, 2. Uh,
Yes, from 1 to 2. That's good. Uh, is this a triangulation? If I use that arc, 1, 2, 3, 4. I have a quadrilateral. It doesn't look like, but it's not a triangle. It's a quadrilateral. I need to add one more arc. Yes. And the other arc goes, there's actually, there's many choices. Do you have any suggestion what I could do?
2 to 1, but you make a round around the circle first, the
Yeah,
inner
yeah.
circle, and
So
then you draw.
we,
Yeah.
we don't want to take this one because this would be
Yeah.
homotopic. Yeah, that's not. But if we go like around like this, then there's no homotopy. I mean, the homotopies, they fix the endpoints. Yeah. I mean, I could not take that arc and move the point down here. No, I mean the homotopy are homotopies that fix endpoints. Yeah, and there's no homotopy. I cannot transform this arc uh, in into that one by keeping the endpoints fixed. That just doesn't work. Yeah, so I've got two arcs, and before I had a quadrilateral. If I introduce this is kind of a diagonal in that quadrilateral, now I must have two triangles. Yeah, there's one triangle here, you see that? And I have another triangle that goes down here. So the surface is cut into two triangulations, into two triangles. I do have a triangulation. That's good. So you have to be, as I said, a bit flexible with your notion of a triangle. Okay, good. And let's give ourselves a triangulation. Here, I can go this way around, I can go that way around. Do I have a triangulation? This one here is a nice triangle, right? It has 1, 2, 3 edges. And the other one here, this has no, 1, 2, 3 edges. This is a triangle, and that one is also a nice triangulation. Good. If we are more ambitious and we go to more complex surfaces, things start getting a bit messy. I mean, the picture is getting more complicated. Let's say I give you some arcs. I mean, there's an arc 1 that goes underneath and comes back here. There's an arc 4 that starts here and goes down there. And there's some other arcs. Is this a triangulation? I think so. It looks like, I mean, I can try to follow. I start here. I follow along the arc 1 and I move along. I come back here. Then to complete it to a triangle, I mean, I have this side of the arc, so I keep the same side of the arc. So I continue with the next possible arc, number 4. I can I come down here, I feel the same side, so I go to the next possible arc, and probably you don't see anymore, but I followed 1, 2, and 3 arcs. I come back. This is a triangle, okay? But it gets a bit complicated. In my uh, my ability to draw those triangulations is limited. Yeah, gets a bit messy. So let's first get one thing out of the way. This is it's a classical result in topology. They formulated in this paper by Fomin, Shapiro, Thurston. When we do have a triangulation of such a marked surface, then the number of internal arcs. Did I say what is an internal arc? An internal arc is one which is not a boundary arc. So I have 1, 2, 3, 4, 5, 6 boundary arcs and 3 internal arcs, okay? Good. So the number of internal arcs in any triangulation is constant. It's always the same number. It's a number n, and this number is given by the following formula. So it's 6 times the surface plus 3 times the number of boundary components in my marked surface plus the number of marked points, subtract 6. Okay? Uh, that's what it is. Yeah, I mean you can yeah. You might be able to play around with this formula and derive Euler's formula for the number of edges of a cube, for instance, because yeah. Anyways, let's verify this formula just to be sure we made no mistake. Yeah. So n is 6 times the genus. Okay, what is the genus here? In our examples, the genus here was 0. The genus here was still 0. And in that example, the genus was 1. The number of boundary components here was 1. We cut out one disk. The number of boundary components here was 2. And the number of boundary components here is 1. So what would our number n be in that case? According to this formula, what is the formula saying? 6 times the genus, which is nothing, 3 times the boundary components, plus number of marked points minus 6. So n in the uppercase would be number of marked points minus 3. So you always have a triangulation of a polygon that has 3 internal arcs, 3 diagonals less than the number of edges, than the number of corners of your polygon. This is a well-known formula, okay? And you can generalize this formula to other shapes. Yeah, so for instance, for the annulus, the formula tells us the number of internal arcs that you need is 2 times the number of boundary components, so it is 6, plus number of marked points minus 6, so it is just the number of marked points. So if you got 2 marked points, you're going to have 2 internal arcs. If you got 1, 2, 3 marked points, you're going to need 3 internal arcs. So this is a fair check to see if we got an actual triangulation. And let's move into this case here. Our formula for n would be, the genus has changed. So 6 times the genus plus 3 times the boundary components, so plus 3, plus number of marked points minus 6. So the number that we want to get here is 6 minus 6. This is going to be number of marked points plus 3. We have got only 1 marked point here, so we need 4 internal arcs. So if I made no mistake, the number at least is correct. So I have a 1, 2, 3, 4 arcs here. That has good chance of being a triangulation. Okay, good.
I have a question, Thomas.
Yeah.
In the example of the annulus, is the arc that starts and ends at 1 and loops around the inner circle, is that a valid arc?
The short answer is no.
Okay.
You mean this arc?
Yeah, like
This arc
yes.
is homotopic to the boundary arc,
Mm-hmm.
and the boundary arc is already there. I mean, I didn't specify them. I mean, I always have the boundary arcs. They are already included. They are already there. These two, the 2 boundary arcs, they are kind of always there in any triangulation. So we have this already. You cannot add that one, right?
Mm-hmm. Okay, yeah, thank you.
So what is your, sorry, the answer to your question? Yes, it is a valid arc, but we have it already.
Yeah, like I was going to say, why
Yeah.
can't, because why can't we add it to the maximal collection? But then, yeah, it's not.
And
it's already there.
and that formula counts only the non-boundary
Internal
arcs,
arcs.
the internal arcs. Yeah, that's it. Yes, there was another question.
Yeah, so in the case of the disk, why is the number of boundary components 3? I somehow missed it. Probably it's a stupid question. So so we got the disk by cutting one disk from the 2 sphere, right?
Exactly. I take the 2 sphere. So this is a two-sphere. Our drawings are really a shortcoming. I mean, this looks like a disk itself. You think this is a three-dimensional object. This is
Yeah,
S2, the two-sphere, okay? From the two-sphere, you cut out a disk, okay, good?
yeah.
And then you kind of want to pull this down. You project everything to the plane, and then you get the actual disk.
Yeah. So, why is the number of boundary components 3?
The boundary components is only the boundary of the disk. We cut out one disk, so there's one boundary component.
Ah, okay.
Yeah.
Sorry.
Yes. No, this is very good. I mean, the boundary component are really just the boundary of the disks that we cut out. We cut out one disk, so there's one boundary component here. That's good.
Okay.
Good.
Thank you. Thank you.
Okay, that's good. Then let's move on. So there's a nice formula for the number of boundary components, and so we are interested once we fix a triangulation, we are interested now in some notion of mutation. Yeah. So the notion of mutation is, the definition of mutation is the following one. This is given here. And suppose we have a triangulation gamma fixed. We have one triangulation gamma, and we consider one gamma one internal arc of that triangulation. Yeah. It's important that the arc gamma is not considered just by itself, but it's an arc that is part of a fixed triangulation gamma. And since we have a triangulation, this gamma must be part of two triangles. Yeah, this must be an edge of two triangles. So gamma is part of a triangulation, so there must be exactly two triangulations that have gamma as an edge. Okay? Because we are in a surface, there cannot be a third triangle sticking out in space or something. Yeah, I mean, there's exactly two triangles neighboring gamma. If you have an orientation, there's the left triangle and the right triangle to gamma. Okay, good. And now these two triangles, they together form a quadrilateral. This one here. Yeah, just the union of these two triangles, they form a quadrilateral. Gamma is one diagonal of this quadrilateral, and there's another diagonal of the same quadrilateral. So my mutation is simply I flip the one diagonal to the other diagonal. Yeah, I switch gamma for gamma prime. And this is called, that's good. And this I would then call a mutation of the triangulation at that arc gamma. That would be the new triangulation mu gamma of the triangulation gamma, where we remove gamma and we add gamma prime. So as we did in cluster theory in cluster sets, we remove one guy and replace it by a different one. Okay, good. And good thing is we always keep the same number because any two triangulation have the same number of arcs. So that looks very much like a cluster setting. Yeah, we have a constant number of elements in every of those triangulations, and I can mutate one to a next one. Okay. Okay, here are some examples. Okay, so this is now the exchange graph, meaning the flip graph, the exchange or the flip graph for the hexagon. I did the work for you. I draw it already, so I can start with any triangulation of the hexagon, like this one. Like I take these three arcs, internal arcs. This is a triangulation. Then I could flip the lower arc to this one. Then I did a flip, a mutation. I can flip the upper arc to that one. This was a mutation. I can, in that situation, flip the lower arc, or what? No, the upper arc, and so on. So I get kind of a commutative diagram of flips, and in that shaded region here, I always keep the middle arc. Yeah, so in these are all the triangulations that contain that middle horizontal arc. Yeah, and I can move on. There's another shape, and common to all these five is they all contain this arc, and they in here they all contain that arc, and so on. So I find all possibilities, all triangulations of the hexagon. There are how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And they are related by flips or mutations in that way. So you can do that relatively easily. I find that actually easier than computing the exchange graph for the cluster algebra. Yeah, I mean that's very visual. I think this is easy to do. Okay, that's fine. Let's be a bit more ambitious and say we want to compute the exchange graph for the annulus. Say we start with this simple annulus that has got just 2 marked points and therefore 2 internal arcs. That's what we computed before. So can you help me? I mean, let's say there's an arc number 1 and an arc number 2. They're very small. Can you see them? Sorry, this is my parents' phone. There's an arc number 1 and then arc number 2. What happens if I flip arc number 1? Okay, I can help you. I do the easy part. If I flip arc number 1, I will keep arc number 2. Good. That was the easy part. Arc number 2, I keep it. What happens to arc number 1? I first have to specify what is the quadrilateral. Maybe this helps. The quadrilateral, I mean, if I remove this one, yeah, then I would, yeah, it's hard to see. If I remove the arc number 1 here, this is a diagonal in a quadrilateral that has these sides 1, 2, 1, 2, 3, and I go back here with 4. I'm a bit confused. Can you complete this 2A triangulation?
We were counting one twice while drawing that. Once from this side and once from the other side. So is it a quadrilateral anymore?
I'm not sure. I'm a bit confused. So let me draw this arc. It's really hard to draw. 2. Okay, let's try just to find another arc that we can fit in here between these 2 marked points. So instead of instead of starting in the same parallel way, I would use something homotropic. I kind of have to make one more round. So I think I can go here, and then I come here, then oops. I go around here, then I already made one more round than the arc 2 is doing at this point. And then I continue going parallel to 2, and I end up here. That is a triangulation, and it works fine. Let's do the easier direction. So, I mean, this was a mutation in this was a mutation of 1. Let's mutate 2. This is easier. Okay, if I mutate 2, I keep 1. And what is the mutated 2?
Is this like in the first picture that you just drew?
Yeah,
Are they homotopy equivalent?
they're not supposed to be. Uh, there's a better way to see this. Let me finish this. So the mutation of 2 would go the other way around, right? Here. And then I keep going. I rather prefer to do these pictures not on the annulus but on the actual cylinder. So let's look at the cylinder. This one, good. And the cylinder, these arcs 1 and 2, the arc 1 goes straight down and the arc 2 goes once around the cylinder. Okay? Good. Now there's a general theory of how you can act on those marked surfaces. Uh, there's something called a mapping class group which acts on such a marked surface, and you can always cut such a cylinder and apply a 360-degree rotation. This is called a Dehn twist, and then glue it back together again. Yeah. And this is kind of what we do under the action of that arc 2 here. So I replace 1 by another arc which is not 2, which has not 1 round. I mean, 1 has 0 rounds. The arc 2 has 1 round. I want now to add an arc that goes twice around the cylinder. So if this one here was 2, I find the new mutated arc 1 as the arc that goes once, twice around the cylinder. If I go twice around, this is not homotopic to going once around. Yeah, because I need to fix the endpoints. Yeah. So whatever I do with my homotopy, the winding number going around the cylinder 1, 0, 1 or 2 times in that direction cannot be changed under homotopy. So this is really what I need to keep track of. I mean, the arcs in general look very complicated. They, if you move further out, they're gonna go 5 times around and then to the boundary point, and then 6 and 7, 8, and so on. So the exchange graph is really indexed by the integers. Yeah. So I can start from here and I go positive or negative rotations of 360 degree, and I change my my triangulation. You see a little bit what's going on?
Yeah.
Good. And but you're right. I mean, this is already not very convincing. It's kind of better if you visualize it on a cylinder and you turn. That's okay. Good. So that's good. So what do we have so far? We have altogether, I try to recollect what we have. So there's a system of arcs in the surface. They have fixed size. There's the boundary arcs and the internal arcs, and for the internal arcs, this is the number n that we computed. They are all arcs. Let's say we call internal arcs. They are grouped into subsets of fixed size n, and each of those sets is a triangulation, okay? And so for every member of such a subset, of such a set, of such a triangulation, I have got a mutation that exchanges the arc gamma to some other arc gamma prime. So that looks very much like cluster algebra combinatorics, but in order to define a cluster algebra, we need a quiver. Yeah, a cluster algebra by the very definition is given by the datum of a quiver or of a skew symmetric matrix, if you wish, but we need that starting, that datum to start a definition of a cluster algebra. So we need to give ourselves a quiver, okay? So how can we do that? The aim now, in the next definition, we fix a triangulation of the marked surface, and we want to define the quiver of that triangulation, Q of gamma. Good, so this quiver is defined in the following way. The vertex set of the quiver is indexed by the arcs. So I take the arcs as the kind of the vertex set of the quiver. And then when is there an arrow between two arcs? And when is there an arrow in the quiver between two arcs? Yeah, when these two arcs, when they are the edges of a triangle, when both of these arcs appear as edges of a triangle, and say gamma I is predecessor of gamma j here in clockwise orientation at the vertex where they join. I mean, if they are edges of one triangle, they join at a common marked point. And when gamma I is predecessor of gamma j, then I would draw an arc in the quiver Q. That's what I do. Notice here I really use that that I have an oriented surface, yeah. So an oriented surface allows me at any local neighborhood of a point to say what is clockwise or counterclockwise. I do have an orientation, yeah. Here I really use that, yeah. If it would be a Klein bottle or something, I couldn't define that quiver. Okay, so that's good. So we use that we have an oriented surface. That's a quiver. Let's do some examples. Okay, let's start with the first example here. What is the shape of the quiver that I get? Can you tell me? You're too shy. Shall I do it for you? So
A triangle?
the points of the quiver correspond to the arcs. So for each arc I get one vertex in the quiver, and then I just connect when two arcs are joined at a joint vertex. I connect them clockwise, and that's it. That's all. There's no more.
A3.
It's A3, yes. So exactly, thank you. So my quiver is 1, 2, 3. If I label my arcs as 1, 2, and 3, this is the quiver. That's okay?
When you're considering arcs, you're only considering the internal arcs and not the boundary ones.
Yes, 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 yes. Yes, you're totally right. I already, I forgot to mention this already here. Yes. So the quiver, the vertex set is gamma is the set of internal arcs.
Can we say that, like, if we put mark points on a circle, then on a disk, then we get a mutation of some an, like
Yes.
in general.
Yes.
And
This
it also
is correct. Yeah.
coincides with the fact, like, initially we had Grassmannian of n plus 3 for an, and here we have
We
m
can
minus 3.
yeah. We produce the same picture for the Grassmannian, for the polygon. We produce the same combinatorics here. Exactly, yes. That's right. Yes, thank you. I will come back to this with some example. That's okay. Good. So thank you for the remark here. You're totally right. I only consider the internal arcs as the vertices of this quiver. Yes, thank you. That's good. So I consider only 1, 2, 3, and no, not anyone else. Okay. Now, what about the second example? In the second example, I got 3 vertices, 1, 2, and 3. Okay. call them 1, 2, and 3. And now I connect them whenever two of those edges join at a joint vertex, I connect them clockwise. So how does the clock go? The clock goes from 2 to 1 this direction, it goes from 3 to 2 this direction, and it goes from 1 to 3 that direction. Is this correct? So the quiver here would be the quiver 1, 3, 2, 1. So now I got a 3 circle, okay? Yeah.
Sorry, so isn't this anti-clockwise?
Um, how how does your clock move? Your clock moves this way, right?
Yes.
Okay. So if I consider the arc 2 and the arc 3,
Hmm.
right?
Okay.
And
Okay.
they are joined at this point,
Hmm.
yeah? So which one is the first in clockwise direction? The clock moves in this way, isn't it?
Yes.
Yeah.
Okay.
So this arc clockwise is that, this arc clockwise is that, and clockwise this arc goes in that direction. That's good?
Okay. Okay. Thank
So
you.
unfortunately, this means that the circle turns the other way around. Yes, I know, I'm aware of this. Yes.
Thank you.
But it fits my definition. That's okay?
Yes. Yes. Yes.
Okay, good. Uh, is your generation used to clocks anyways?
Yes. Yes.
Because, sorry, this is really not relevant. My son has this nice big round clock on top in his kitchen. Yeah, and I told him that the time it shows is not right. And he's like, what? This is a clock. He never considered this as showing the time because time for him is something like this. Yeah. So, okay, sorry. But we know what is clockwise and counterclockwise. You agree?
Yes. Yes.
Good. Here are some more interesting examples. Let's look at that. Okay, good. You agree that our quiver here has got two vertices because we have got two internal arcs. So there's an internal arc 1 and there's an internal arc 2. So if I do this slowly, I go from what do I want to do? These two arcs, they join here at a common marked point. And clockwise means there's an arrow from where to where?
One, two,
Left.
I go clockwise, I go from 1 to 2. That's okay?
Yes.
Good. And now look carefully. I mean, the same two arcs, 1 and 2, they are also part of a triangle and they meet at this mark point, right? Okay. And if I focus on that mark point, there need to be an arrow from where to where, clockwise?
1, 2, 2.
1 to 2, again. Yeah. So there's an arrow from 1 to 2, and there's an arrow from 1 to 2. So the quiver is this one. You agree? Okay, good. So this is what is, you saw it already. This is called the Kronecker quiver. So we get the Kronecker quiver from an annulus with two marked points, one on each boundary component. Good? Okay, good. And then, well, I mean, this is now just a fun exercise. I mean, if I call these arrows like 1, 2, and 3, I would go from 1 to 2, from 2 to 3. But they also, 1 and 3 also meet here, and the clock runs in this way. So the quiver there would be something like 1 to 2 to 3 and 1 to 3. Okay? So you can produce these quivers. Here you're comfortable with that. That's okay? Good. Questions? You're fine? Okay. Okay, so let's where are we? What did we achieve? we define a quiver. Okay, good. If we want to use this quiver for a cluster algebra, you remember in cluster algebras, this need to be a quiver that has no loops and no two cycles. Yeah, otherwise our mutation would not be well defined. Yeah. So let's verify that our quiver Q gamma has no loops and no two cycles. Good, good, good. So, but what would be a loop? I mean, a loop would be locally such a situation where the same arc gamma I is adjacent to a marked point. Yeah, and there's nothing in between. So that would be a loop from I to I. But we said we exclude this situation. Yeah, in our definition of an arc, that arc would be contractible, and we said that's not allowed. Okay, so we have no loops. And a two cycle would coming from a situation where you have two arcs, gamma I, gamma j, and they intersect in one marked point once here, and then the same two arcs intersect in another marked point in the other way around. But then we have that gamma I and gamma j would be homotopic. Yeah. And we say we don't consider two copies of one homotopic arc. So this one can also not occur. So therefore, we have no loops and no two cycles. We have a good quiver. We can define a cluster algebra now. Yeah, so given a triangulation of a surface, we can define a cluster algebra using that quiver. That's what we do. Okay, fine. Now, yeah, so dilemma implies we can use the Fomin-Seliwinski notation to define a cluster algebra. Let's call this cluster algebra A of that quiver. Okay. So can we understand the flip of an arc in terms of mutations of that quiver? Let's try to analyze this one here. Sorry, I'm not following the chat too closely. Aditya in the Konica quiver. Yeah, why it looks like they go the other way around, right? But I mean, it's the same game. I mean, I have this one arc and the other arc, 1 and 2, and they are joined, they meet at this point, and then I go clockwise, and my clock moves like this. Yeah, so I have to go in that orientation. Now, this was if I zoom in the neighborhood of that point. Yeah, this is a local property. Now I zoom in the neighborhood of this point. In the neighborhood of this point, it looks like the arc 1 is here, the arc 2 is there. They meet at the joint vertex, and clockwise, 1 is a predecessor of that arc, which is the arc 2. Yeah. So I apply the same rule here. That gives me two arrows in the same direction. I'm sorry. This is just what we get. Yeah. That's okay? Thank you. So can we understand flips? So let's do this. Fumin, Shapiro, Thurston showed that a flip of an arc in a triangulation is the exact same as the mutation rule of the at the vertex gamma in that quiver. Okay? So let's try to understand this. What is the flip? The flip is we have the quadrilateral formed by the two triangles adjacent to gamma. And the flip would be that we replace this diagonal gamma by that diagonal gamma prime. Okay, so what happens on the other side? What happens on the side of the quiver? Yeah, so I take these two and I construct their quivers. Yeah, so the quiver for the upper part would be along gamma. We have one of those oriented cycles of length 3 as we constructed it earlier. Yeah, so I go clockwise around here, I go clockwise there, I go clockwise there. This gives me these 3 arrows in that direction, and symmetrically on the bottom, the same thing, yeah. And if I play the same game for gamma prime here, yeah, there are the same triangles giving rise to 3 arrows clockwise like this, clockwise like that, clockwise like that. So that's the situation locally around gamma and gamma prime here. What was the what was the mutation at a vertex gamma in the quiver? How did we compute that again? We want to introduce an extra arrow. There's a path of length 2 going through gamma. We want to introduce an extra arrow up here. Then we flip the orientation of these two, and then we delete this 2 cycle, right? Good. So if I look down here, what has happened? Both these arrows have turned the direction, and there's nothing here anymore because I deleted the 2 cycle. So this is what the mutation does. Just like this, you can verify by hand. Yeah. Are you convinced, reasonably convinced, the flip really is the mutation on this side? Questions? We're good. Okay. So let's summarize what we have. Okay. So this is the theorem by Böhm, Shapiro-Thurston. Suppose we have a marked surface. First thing, this is a fact from basic topology. Any two triangulations, gamma gamma prime of the same surface can be related by a sequence of flips. So you give me 2 triangulations, then there exists a finite sequence of flips that transforms gamma into gamma prime. Any 2 triangulations are flip equivalent. Yeah. So kind of in cluster combinatorics, these exchange graphs that you see here, they're always connected. Yeah, you can go from any triangulation to any other triangulation. And this has as a consequence that the cluster algebra does actually not depend on the choice of the triangulation gamma, because I mean I could start with any gamma, and then I will, as cluster variables, obtain all the arcs that are contained in any other triangulation. So if I start here or if I start here, I get the same set of cluster variables, and they are grouped into the same set of clusters, yeah, the triangulations. So it doesn't matter where I start, and I might equally say just this is the cluster algebra of the surface, you know. You can choose any initial seed if you want by this quiver and keep going, but you're always going to get the same cluster algebras, yeah. And maybe we summarize what we have. Under our combinatorics, we see that the triangulations of the surface, they correspond to the clusters in that cluster algebra. The flip corresponds to mutation. This is what we said. And the set of all cluster variables is the set of all variables that are obtained from an initial cluster by doing all mutations. But if you do that, you will exactly produce all possible arcs, because we said in the beginning any arc is contained in some triangulation. Yeah. So it must be reached by iterated mutations at some point. So the set of arcs, did I forget to write internal? Kind of for me an arc is okay, internal. Good. The set of internal arcs corresponds bijectively to the set of cluster variables. And okay, then you can ask yourself how many cluster. Okay, so this exchange graph here for the hexagon was a finite graph, but for this one, and by the way, we computed that. Here the quiver would be the Kronecker quiver, and we do know this is representation infinite. So we do get infinitely many, so infinitely many cluster variables. And in fact, you do get finitely many cluster variables if and only if this is a polygon. So the polygon is the only case where you have finitely many cluster variables. Okay. All other cases, you have infinitely many cluster variables, you have infinitely many triangulations. You can play this game of the cylinder. You apply rotations and you create infinitely many new arcs. Okay, so this is good. Can you give me 1 minute break, please? There was a question. I have to answer this. Sorry.
Sorry, it was a small question. So,
Yes.
did I understand correctly that if the genus of the surface is more than one, then there will be there will always be infinite number of cluster variables.
Yes, always.
So, because a polygon can come only from S2, right?
Excuse me.
So a polygon can come only from S2, right?
Yes.
Okay, thank you.
So if you have if you have a surface of any other genus than 0, it is automatically infinitely many cluster variables. And even for genus 0, there's only one way to get finitely many. This is only if you cut out one disk from the sphere. Yeah. So if you had a sphere and you cut out more than one disk. If you cut out 2 disks, you get a cylinder. If you cut out 3 disks, and you have some mark points, there's already infinite number of arcs that you can create. Yeah. I mean, you can go a million times around here and then you end up at the other. You can do many circles, however you wish. Yeah. It will always be infinite. Okay, that's good. So Regio already indicated this looks like something that we did earlier for the polygon case. And I want to address this. And there's a kind of a geometric realization of those cluster algebras. And this also answers to a request of Amit. I should say something about the history of those geometric realizations. So let's go far back in history to the wise mathematician Ptolemy, who was living from 170 to 100 AD. Okay. And he told us in his original language, no, I don't speak Greek, but I translate to English. So when you have a cyclic quadrilateral, when you have 4 points sitting on a cycle, then the product of the lengths of its diagonals the product of the lengths of its diagonals. So say the diagonals are gamma and gamma prime, and the product of their lengths is equal to the sum of the products of the opposite sides. So this is equal to the sum of the products of the lengths of the opposite sides. So Ptolemy gave us this relation for the lengths of diagonals on a cycle, okay? And this is the exchange relation that we have in this cluster algebra. I mean, instead of the arc, I consider the corresponding cluster variable, and they are exactly following this rule. Yeah, and if you happen to have a polygon whose side lengths are unit lengths, are lengths 1, then this is also correct if you include the boundary arcs. So the cluster mutation really follows the Ptolemy relation. So it kind of goes back 2000 years. I'm sorry, this is a bit of a joke, but it is true. I mean, that was maybe the first root of cluster algebras, if you allow me to say so. That's okay. And then we want to generalize from the disk to surfaces, and things don't go quite so well for surfaces. The just the length of an arc. I mean, first the diagonal isn't so well defined anymore. On a torus, what is a diagonal? You need to choose a geodesic. I mean, a shortest path curve, right? And the lengths actually do not behave like Ptolemy told us if you are on different surfaces of different genus. You can get around this by a story that Penner has investigated in the 80s. In 1987, he found some way to kind of recover that that formula for the lengths. But you need to introduce a different metric on your surface. So this is what is called Penner coordinates on the Teichmüller space. The Teichmüller space is the collection of all those possible triangulations, if you wish. So he introduced a different metric on the surface that turns the marked points into cusps. So the marked points, they are kind of sitting at infinity. Yeah. The distance between two marked points is kind of infinite, and then you ask yourself, why would I create a metric where the distance is infinite? I mean, I want to measure actual length, right? And yes, he then, when you have an arc, when you have an arc between two marked points, so the arc would approach this point at infinity at some point. And then you would, when it is small enough and you are not in the neighborhood of any other points, then you would cut a little circle around that cusp in a geodesic way. So they are called horocycles. Sorry for the words. This is how they call them. And then you compute the length of gamma starting only from this horocycle and going to the other horocycle here. And those systems of lengths up to some normalization satisfy the same equation. That's what he showed. Yeah. So those equations that govern the mutation of cluster variables for the cluster algebra given by a marked surface geometrically can be realized using Penner's metric and Penner's method to cut those arcs so that they have finite length. So kind of, but this was also 1987, so this predates any cluster algebra. So this is just to tell you that those considerations for a large class of cluster algebras, they have been already around. Yeah. So this is my history part. That's okay for now. Yeah, I will come back more to more recent history. So what do we have now? We have a nice cluster algebra for any marked surface. We understand a little bit what are the clusters, they are triangulations, what are the cluster variables, they correspond to arcs, and we know how to mutate an arc in a given triangulation. And what I really want to come to now is the gentle algebra. So gentle algebras is, I think this was even in the title of my lecture notes, so I have to come back to gentle algebras. Amit was talking last week about string algebras. And gentle algebras are a special case of string algebras. And I think you did not really define gentle algebras, did you?
No, I did not.
Okay, good. So they will come today. So what we have so far, given a triangulation, given a triangulation of some marked surface, what we have so far is the quiver. Okay. Now I want to turn that quiver into an algebra, into a bound quiver. So I want to add some relations. Good. And just how do we, what is a good way to do that? And we have done this in a joint paper with Ibrahim Assem. Assem was the one who invented gentle algebra, so this goes in the right direction. And at the time, two of our students, Gabriel Charbonneau-Chaudouin and Pierre-Guy Plamondon, and it has been done also by Daniel Labadini in a more complicated case when you allow punctures in your surface. So we consider the unpunctured case. And so here's the thing. We have the triangulation, we have the surface, we know how to construct our quiver. We want to add some relations. The quiver is the one that we have. And which set of relations do we want to add to this quiver? We want to consider the ideal which is generated by all paths of length 2, alpha, beta, beta, gamma, gamma, alpha, whenever there's a triangle of internal arcs in the triangulation. So you remember before in the hexagon, we had the situation we could possibly define a triangulation like this, where there's a triangle that consists only of internal arcs. Yeah, whenever such a thing happens, then we compute it. We do get a 3-cycle in the quiver, and I just request that any two consecutive products in this 3-cycle are 0. This is my set of relations. Simple as that. That's okay. Good. So in the meantime, there has been developed a more general stories by people coming from physics. They would consider a potential on this quiver as being the potential W would be the sum of all the 3 cycles. So this is one 3-cycle, and then our algebra that we consider here in their language would be the Jacobian algebra. So you take the derivative of those 3 cycles. So when you have a 3-cycle alpha, beta, gamma, and you take the derivative with respect to alpha of alpha, beta, gamma, that would give you beta, gamma, isn't it? And so they take formal derivatives in all 3 variables. So what they end up with is alpha, beta, beta, gamma, gamma, alpha. This is what I have told you. This is what we want. Yeah. So there's some different, more general language of quiver with potential in Jacobian algebra, and it gives us exactly that. That's good. Okay. And then when we have our arbitrary triangulation of a surface, then this algebra is a gentle algebra. Okay, so what does it mean, having a gentle algebra? It means that first, at every vertex of the quiver start and end at most 2 arrows. So if we have any vertex here given by gamma, there's at most 2 incoming and there's at most 2 outgoing arrows. Yeah. And also for every arrow beta, there's at most 1 alpha that I can compose it with without the composition being in the ideal from the beginning and at the end. So there's at most 1 arrow such that the product alpha beta is non-zero, and there's at most 1 arrow gamma such that the product beta gamma is non-zero. So these two conditions together should define a string algebra. Am I correct? Okay, good. So the algebra that we have here is a string algebra, but now I add two more conditions, and these two more conditions then make a gentle algebra. Okay, so the other condition looks pretty similar, but this time around I say for every arrow beta, there's at most one alpha, such that the product is in the ideal. So look, if I have an arrow beta and there's two arrows alpha and alpha prime going in, then before we said there must be at least one relation. So there's only one product surviving, but now we say there's also at most one relation. Yeah. So there is exactly one relation. When you have a situation like this, two arrows enter in one arrow beta, there must be precisely one of the products zero. It cannot be that both products zero. It cannot be that both products are non-zero. Precisely one of the two must vanish. Yeah, and this is for ingoing arrows to beta and for outgoing arrows from beta. That's good. Okay, and finally, these are all the relations that you're generating gamma, the ideal. Yeah, there are no longer relations of length 3 or 4 or something else. Okay. So an algebra satisfying these four conditions is called a gentle algebra. And maybe I should give reference to Assem and Skowronski. They were the ones who defined this in I forgot, around in the 80s, okay? Good. Okay, proof. Okay, so here's the definition, but there's the statement. This is a gentle algebra. Okay, let's prove this. And the proof is here. You see my proof? Okay, good. I mean, being gentle is a local condition. I mean, around the neighborhood of every point, gamma, there's some condition on the arrows and composition of arrows. So it's sufficient to check this really locally. I don't care what happens in the rest. So for every gamma, I need to verify. And as you see, the maximal situation that can occur is this one. There's two arrows going in and two arrows going out. It might be one of these arcs is a boundary arc, then forget this, then delete this, okay? Then there's only one arrow going in, this is allowed, yeah? So of these four arcs here, some might not be present, that's okay. The maximum possible situation is they are all there. Then we have two incoming and two outgoing arrows. And you do see that if I go in here, exactly one relation is there and the other one, there's no relation, yeah? If I go in with this arrow and I can continue here without a relation, I can continue there with a relation. So precisely one of the two products vanishes. This is the condition for being gentle. So we have a gentle algebra, do we agree? Okay. And then so this was in 2008. And I presented this construction at the ICRA conference, which was in Torun in 2008, a nice city I would recommend to visit. And I gave my presentation, and then I got the question, do we get all gentle algebras in this way? I mean, what we prove is we do get some gentle algebras, yeah? And the question arose, the question came from the audience, do we get every gentle algebra in this way, yeah? And I said, no, of course not. I mean, look at it. I mean, the only relations that we obtain come from these three cycles, yeah? So we get, which gentle algebras do we get? We get precisely those gentle algebras where all the relations lie on a three cycle. Yeah, so a gentle algebra that we get from that construction, from a triangulation of a surface, is is obtained by a graph coming from the surface. And whenever I have an internal triangle, I do have a cycle, a 3-cycle, and in the 3-cycle I have iterated relations of length 2. So I have one such situation here corresponding to that internal triangle, corresponding to this internal triangle. I get another 3-cycle here. And the general algebras that I do obtain from surfaces, they look exactly like this. Yeah, there's a 3-cycle with all 0 relations. There might be another one. There might in general be, in general, I might have more 3-cycles, all with 0 relations. They might be connected. I mean, the surface might go around in the back, so the graph might be connected in very complicated ways. But that's really what it is. I have those groups of 3-cycles with 0 relations, and they are connected by sequences of arrows without any relations. That's what it is. Yeah. Good. So so this was my answer to the question, do we get all gentle algebras? My answer was no, of course not. We only get those that look like this. Yeah. And you know, this was in 2008, and I was a little bit younger, and maybe I was lacking some wisdom at the time. So, like any of those questions you get is a good question. It should give you some incentive to think about it. Yeah, I mean, I could have started asking myself the question, yeah, but what can we do to generalize? What can we do to obtain all gentle algebras? Yeah, but I was really stuck in my mind that no, this is not possible. You don't get all of them. Yeah, and then fair enough, other people started thinking about it, and they were able to create all gentle algebras from some configurations of arcs on a marked surface. Yeah. So I would like to encourage you to be open. This is the moral of the story. Whenever you have some question, be open and think about. Let the question talk to you. Don't refuse. No, I'm stuck in my knowledge. That's what I get. Let the question talk to you. Maybe there is some way, even if you don't see it at this moment, maybe it can be done. Yeah. So I will be happy to present you this in what in the following, but at the time I wasn't ready for this. Good. So this was my little moral for today. That's okay. Okay, we had yesterday and day before yesterday we were talking about categorification. So I would like to bring categories into play now. This will be helpful. Yeah. And I have to go a little bit more general now because the algebras, the quivers that I have, they are quivers that have oriented cycles. And what we did so far, we had a quiver without any oriented cycle, yeah, to define a cluster algebra. So, but I can tell you there is a more general construction by Claire Amio that can produce a cluster category also for those kind of algebras. Yeah, it's a kind of a complicated construction. I don't go too much into detail, but you can compute, you can define for any marked surface and any triangulation, there exists a cluster category, and it satisfies the same properties that we had, that that the cluster variables, no, that the clusters in the cluster algebra correspond to the cluster tilting sets in that new category, that the mutation in the cluster algebra corresponds to some mutation that you can define for objects in this cluster category, and the set of all cluster variables in the cluster algebra corresponds to all rigid indecomposables which are obtained by a finite sequence of mutations from some initial cluster, and this is called a reachable. Yeah, so there are these nice bijections that we had seen when Q is a Düngen quiver, and it is valid when Q is an acyclic quiver, And in the situations we consider here, Amiot was able to show in general for two Calabi-Yau categories that you do have a category that satisfies these nice bijections, okay? And these nice bijections, they go all the way to what we have already established before. So these indecomposable rigid objects correspond to arcs, cluster tilting sets to triangulations, and mutation is a flip. So you can really relate these three things. And moreover, we have the same formula that we had yesterday. If you take this cluster category and you divide by the additive category generated by such a cluster tilting set. So we delete kind of indecomposable objects which form a cluster tilting set. Then we do get an equivalence to the module category of this algebra, of this gentle algebra that we defined before. Okay. So that's a kind of a repetition of the same result holds here that we had yesterday. The cluster category factor out a cluster tilting object is equivalent to the module category. The good thing here, and now this starts getting interesting, the good thing here is that that is a gentle algebra. And Amit mentioned, or he explained last week, that for gentle algebra, these are string algebras. For string algebra, we have a full classification of the modules. We can describe all the objects here by something called string modules and by some procedure starting with something called band modules. Yeah? So that has been established by Butler and Ringel already in the 80s. We do know all the modules here, and there's a nice combinatorics. The indecomposables are given by string modules and band modules. So why not use that information if we have this equivalence of categories? I told you in general, they are both infinitely many cluster variables. So up to a finite number set of objects that we can control very much, they are just the arcs in the given fixed triangulation. Up to those finitely many, we have a bijection between the indecomposables here and the indecomposables here. So we can, without going into the detail of this construction, which is complicated, we can combinatorially understand the objects of this category because we understand them on this side. And up to finitely many, there's a bijection. Yeah. So there must be some combinatorics in this cluster algebra that is governed by the combinatorics of string and band modules. That's the main idea for now. That's okay? So this is what we then try to establish when we have a triangulation of the surface, then really there is a bijection. So this really comes from here. So there's a bijection between the strings in this string algebra here. Yeah, the notion of strings. So the strings here correspond bijectively to curves in the marked surface. Yeah, they correspond here to curves, but not curves that come from our fixed triangulation gamma. So they correspond to curves in the surface that do not belong to the triangulation gamma. And on the other side, such a string gives rise to a string module, an indecomposable module over this algebra. So there's a bijection between the indecomposable string modules, strings, and curves gamma in the surface that do not belong to the original triangulation. Okay? So that's really, maybe for me, this is like a start of a geometric realization. Those string modules are tied to actual curves in the surface. Okay, so that's a geometric realization of that category in here. What's the time? Okay, how much time do I have?
You can continue for 5-10 minutes as you wish. We are all here by wish.
Yeah, okay, good. I would like to go through this construction and then this is the most important part for today. Okay, that's good. So let's illustrate this a little bit. If I have a curve in the surface, how do I get the string? The string in this string algebra, okay? That's what I want to do. So suppose I'm given a curve. A curve is not an arc. A curve is just a curve, yeah? So it might have self-intersections, yeah? So assume I have a curve in this marked surface, but the curve still starts in a marked point and it ends in a marked point, okay? And when the curve passes through the surface from the first to the last marked point, it will intersect. I mean, I fix a triangulation. It will intersect the arcs of the triangulation along the way. Yeah, that's what a curve does. And but I mean, it passes through the triangles of gamma. It intersects the arcs of gamma. But remember, the arcs of gamma, these are the vertices of the algebra of the quiver. Yeah. So when I start with my curve here, there's a first point where I hit a vertex of the quiver. Then I move along to the next vertex of the quiver, and I move along an arrow in the quiver. Sometimes in clockwise direction. Sometimes I follow the orientation of the arc. Of the arrow in the quiver. Sometimes if I move with my curve gamma, sometimes I will go the arrow in the reverse direction because this comes from a triangle which goes clockwise like this. Yeah. So what I create, I really create a, a path, a walk in that quiver along arrows or arrows in the reverse direction in this quiver. So this is the first start in the definition of a string, right? How did you introduce strings? These are paths through the quiver where we follow the orientation of the arrow or we allow to go in reverse direction. And this is really what we create here. Do you see that? Yeah. And in order, so now you can help me. Did you pay attention last week? Is any such path, is it a string? No, we have to verify some conditions, right? Uh, what are some conditions that we need to verify? So this gamma determines a walk in the quiver of this algebra. Yeah. So anyone wants to tell me? Is any walk a valid string?
The
Is it this?
edges must not be like belonging to the relation.
Yes, 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 yes. We we have to avoid those zero relations. I cannot walk through a zero relation in a string. Yes, that's really what I need to verify, right? Okay, so what would that mean that I go through a zero relation in that way? Yeah. So the zero relations, you remember, they are only appearing in internal triangles. Okay. So what would that mean? I mean, my curve gamma would enter a triangle. My curve gamma would kind of enter a triangle. Yeah. I hit this arrow alpha, and then I want to continue along the zero relation. That means I would again continue the triangle on this side. You see what I mean? If I want to go along that path, my curve gamma would kind of go along like this. You see what I say? Yeah. However, we don't consider this curve because I can then go right here. I can avoid this path. I mean, I can go along that arrow in the reverse direction. Uh, and we consider arcs up to homotopy, and this arc is homotopic to that arc. Yeah. And I didn't tell you the arc that we had here is homotropic to this arc that goes right through here, and we always choose a representative of our curve which has a minimal number of intersections with our triangulation. Yeah, in the homotopy class, I mean, I would not choose an arc that wiggles around a million times and then leaves the arc. No, I mean, this is stupid. I would choose this arc, right? So, in my selection of arcs up to homotopy, I always choose a representative that has the minimum number of intersections with the given arcs of the triangulation. And so therefore I did not choose this one, I did choose this one. Yeah. And that one does not pass through the zero relation, that just follows the arc here in the reverse direction. Yeah. So we never go through a zero relation in if we follow that construction from a triangulation. That was the important part to check. That's okay?
I have a question. So don't we
Yes.
need to check whether the string is reduced or not?
Yes. I leave it to you as an exercise, or maybe we do it in the tutorial. I would also need to check that I don't use the same arc alpha twice. So when I go with gamma in this direction, yeah, okay. But okay, no, let's do this here. So how could that how could that occur? Let's you give me some more minutes, yeah. So how could that occur that we have an arc alpha here and we would follow the same arc alpha right back? So if my curve gamma goes along alpha, how can I return the same alpha? I would kind of need to go back immediately, right? But if I go back immediately, then I would simply take the curve that doesn't go here. I mean, these two curves would be homotopic, so I can take a shortcut here. It's the same thing, yeah. I mean, going around alpha and alpha inverse means in the surface model, I would find a homotopic arc that doesn't enter alpha at all, yeah. That's okay? Yeah. So, that convinces us that we do have this correspondence between curves in the triangulation that do not belong to gamma and strings and string modules. Okay, good. And I would like to continue with this observation then tomorrow. Let's end it here. Thank you very much.